Alright, so in the previous video, I talked about titrating sodium bicarbonate with an acid and a base. I first showed that due to the competing K values, bicarbonate behaves more often as a base than it does as an acid. And so just as a reference number, because it does depend on the concentration, we started our titration off at a value of about 9, as in something sort of basic. I didn't calculate that out. You can go back and see how to calculate the pH of a weak base. In a previous video, I just used 9. What we did then, though, is we imagined reacting it with NaOH. And as a result, it reacted to form CO3 2-, and then we looked at the pH associated with that CO3 2-, and we saw that by adding the base of NaOH, we drove at equivalence the pH up to 11.66. And then we can imagine the rest of that curve as we add more and more NaOH, and the system becomes more and more basic, going up pretty close to a pH of 14. Now what we're going to do is look at the other end of this spectrum, where we're going to add HCl, and we're going to drive this pH down through a lower equivalence point, and then we'll see, once the HCl takes over, how this will turn into, a strong acid looking like something around a pH of 1. The question is, what's the pH at the second equivalence point, or the other equivalence point, when we make HCO3- act as a base through its reaction with HCl? So there's your reaction. We can see the proton this time is transferring from the HCl to the HCO3- to form H2O CO3, and we can see that in this case the bicarbonate is behaving as a base or a proton acceptor. So let's look at our values. We had 0.2 molar bicarbonate, I believe. Yep, and we had 20 milliliters. And we want to know what's happening at equivalence, so I'll find my moles. I'm going to take that moles and recognize that if it's at equivalence, that's the same as the moles for HCl. Working backwards then, since I'm using a 0.2 molar HCl, I can find my volume. And because my concentrations are the same, this happens to be the same volume, but it wouldn't always, so that's why I'm calculating it. Assuming that these react to completion, then there will be no hydrochloric acid or bicarbonate left over, and it will all be changed over to H2CO3. Again, I'm neglecting my Cl3- because it's the conjugate of a strong acid, so it doesn't participate in any reverse reactions. And now my volume, my new volume total, is the sum of the two volumes that I've added, 0.02 liters plus 0.02 liters, for a total of 0.04 liters. And I can get a concentration after the acid-base reaction happens of H2CO3 that's produced. Going a little bit faster here because I've made a few of these now. So if you want a little bit more description as you're going through, you can get it, but for right now I'm trying to speed up because we're sort of repeating calculations. So what that means then is we have H2CO3, and we can imagine adding water to that, and it is going to act as a weak acid producing hydronium and bicarbonate. I used all of this up, and I don't have any of this, or I'm ignoring the native population. I have a concentration of this of 0.1 molar. Because I have zeros over here, I can assume that my equilibrium will shift to the right. And so at equilibrium, I will have x and 0.1 minus x, although I'll probably use the 100 rule to simplify that. The Ka for the first proton process on carbonic acid is 4.4 times 10 to the negative 7. Did I look at the right number? Yeah. So what that means then if I want to use my 100 rule, if I have 0.1 over my Ka, 1, it's going to be, I don't know, something big, much more than 100. 2 million. That's greater than 100. So that means that this change will be small, which means that this is approximately equal to 0.1. I know I've been using this approximation technique a lot in this unit, and if you haven't seen it, you can go back to one of my previous videos called the 100 rule, and you can go and see why I can make that assumption. But at this point, we sort of assume we know what we're doing here. So my Ka1 expression here is the concentration of my H3O plus times the concentration of my HCO3 minus over the concentration of my carbonic acid. So I got x, 0.1 minus x simplified to 0.1 because of the 100 rule, 4.4 times 10 to the negative 7, and so I can solve this for x. 4.4 exponent negative 7 times 0.1 equals square root that answer, and I got 2.1 times 10 to the negative 4. That's my concentration of hydronium. So I can calculate my pH directly. So I get a pH of 3.68. So that is my other equivalence point. So again, I think this is one of the cooler things. Bicarbonate, because it has room to take on an H if it wants, or because it has an H that it can give up, can act as either an acid or a base. So if you put a base with it, it's going to donate its proton and act like an acid. And if you put an acid with it, it's going to take in that acid's proton and act like a base. What that means then is that because it's more comfortable acting as a base in the first place, it starts as a base. But if we can titrate this in either direction, we can titrate it by adding a base, and we can see that if we do that, we get an equivalence point around 11.66. And if we go the other way, if we push it with an acid to make it more acidic, we'll get an equivalence point around 3.68. And with those two things, what we can do is we can choose indicators that will change color in the appropriate region. So we're kind of used to talking about with our titrations the indicator phenolphthalein. Phenolphthalein changes temperature, changes color right around a pH of 7. Well, that wouldn't be good for this titration because we don't have an equivalence point near 7. But there are other types of indicators, and those other types of indicators change color at different temperatures, or different pHs. So you could find a indicator that changes pH, or changes color around a pH of about 11.6. And that would be a good indicator if we are going to titrate HCO3 minus with a base. Alternatively, you could find an indicator that changes color around 3.68, and that would be a good indicator to see if you're going to titrate HCO3 minus with an acid like HCl. I'm just swinging through the book over here, and I'm trying to come up with a chart of some different indicators and what pH ranges they change color at. In this class, I'm at least currently using the old Nelson Chemistry 12, and so if I find it here, oh, here we go. So let's say I'm looking for something that changes pH around 3.68. I'm titrating with the acid. I could use methyl orange. On page 609 it tells me that methyl orange changes colors between pHs of 3.2 and 4.4. So 3.68 falls in that range, so I could choose to do that if I was using the acid. Alternatively, if I was using a base looking for something that changes color around 11.66, I could use something like alizarin yellow, which will change color between 10.1 and 12. And we can see, for example, that alizarin yellow will go from yellow to red. I might be able to use something like indigo carmine, which will go from blue to yellow in a pH range of 11.4 to 13. So anyways, I can tailor my indicator so that it will change color at the pH of interest. And that way I can do titrations that don't necessarily have equivalence points where their pHs are 7. Again, if you have the Chemistry Nelson 11 textbook, this is on page 609. So that's how you can titrate an amphiprotic molecule particle using an acid or a base and end up with two very different equivalence points.